Good afternoon, everyone, and welcome to today's webinar here at SimScale. Pleasure to host you all. I'm David, I'm co-founder and CEO of SimScale. We're going to get to our guests today, Joel and Sam, in a second. So they're going to introduce themselves in a second in more detail. But before we do that, just a couple of logistical notes. We're using GoToWebinar for the session, and GoToWebinar allows us to record the session. So we're going to send the recording to everybody afterwards, probably in the next 24 hours. And then second, everybody can ask questions at any point in time during the session. So you can just type in at any point in time if you have questions. And I will see if we have time. We can cover them at the end of the presentation. With that being said, let's do a quick test. There's a little functionality inside GoToWebinar where you can raise your hand. Could you quickly raise your hand to indicate A, that you can see the slides, and B, the audio is working well? Could we quickly test that? There we go. Very nice, that works. Appreciate the collaboration for the quick test, just making sure you actually can hear me. Good. Then, without further ado, let's directly dig in. I'll share a few words about SimScale in a second, but I introduced myself already. We're excited to host Joel and Sam today because we're going to talk about accelerating decarbonization, how simulation can be used to accelerate the design of heat networks, of data centers, of placements of air source heat pumps, things that Joel and Sam know much more about than I do. So I'm going to leave much of the talking to them over the next couple of minutes. But I'd love to if we can do just a mini introduction, Joel, Sam, of both of you, if you would quickly introduce yourselves, because I'm excited to have them as experts in this field today, and they're going to share some of the exciting engineering work they will do in a second. But I don't want to just later introduce yourself. Joel, could you quickly start with a quick introduction of yourself, and then we hand it over to Sam?
No problem at all. So thank you, David. So my name's Joel Gustafsson. I'm the director here at JG Consulting. We're an engineering consultancy that specialises in all of the technical issues to do with enabling the energy transition in buildings. And so that largely falls under electrification of heat, the overlap with retrofit, and the generation, distribution, and storage of electricity. We're talking here today specifically about the CFD of air plumes. And we've been collaborating with Sam on this journey for many years, and I'll hand over to Sam.
Thanks, Joel. So Sam Bromley, Director of Element Designs. In this particular collaboration, I'm responsible for the CFD modelling and the geometric modelling of the environments that we're simulating. And also, on the other side of the company, my sort of core work is industrial design for construction and architecture.
Awesome. We're going to hear much more from Joel and Sam for the rest of the sessions. I promise, typically I ramble a lot, but today I actually going to shut up rambling over in 2 to 3 minutes. So I'm just going to do the introduction and then hand over to Joel and Sam. But a few words of why we're hosting this here today. And it really comes down to, for the folks, I think most in the audience know SimScale. Some, I think, are fresh. So just as a recap, SimScale as a company, here's a couple of statistics, a couple of customers we work with. But really, these statistics there on the left around users and projects and simulations shall only convey that for the decades SimScale has been around, we've been fortunate enough to work with thousands of engineering organizations, engineering teams, such as we see here today with Joel and Sam on their simulation strategy, on helping them really simulate, cut down simulation lead time in order to help them innovate faster. That's at the core what SimScale is about. We believe that simulation needs to be done earlier, broader, more intensely in design processes in order to iterate faster and get to a more, a better design, a better location of a heat pump, a better solution in the built environment. And at the core, SimScale is really just an enabler. So it's a new breed of simulation platform that allows to simulate more aggressively. But at the end of the day, it's about the innovation that this new type of simulation allows. And so in the Engineering Leaders series, we try to really set the stage or give the stage to SimScale users, SimScale customers that have been doing amazing engineering work, such as Joel and Sam today, and share a bit of their work they are doing to hopefully inspire others, to help others learn, and to really foster a bit this engineering community around SimScale. For the ones, and that's sort of the last thing, like the last 2 minutes here about SimScale, for the ones that don't know SimScale yet, here's a quick, really the one slide about SimScale. we heard SimScale is about helping engineers innovate faster. How? And that's about making simulation truly accessible. And the way we do that is that's a screenshot of SimScale, actually with hopefully with a relevant simulation we can see there, a bit of external flow around the city and a location of a heat pumps on a roof. Again, we have the two experts here, so I'm not talking about this too much. We're going to hear much more competent words about this in a second. But the unique thing about that is the fact that it all runs in a browser, so cloud native. You can deploy it broadly into engineering teams. You can use it wherever you need to be. You can facilitate collaboration between different stakeholders on a design, on an engineering project. At any point in time, you know how it is, those simulations can be computationally intense. And so when you say, simulate earlier, broader, more intensely, that means you need to provision the required HPC resources at that point in time. SimScale takes care of that in the background. In most engineering projects involve many different types of physics, so all of them are covered. And lastly, because all of the data is being generated in the cloud in structured databases sitting right next to GPUs, SimScale allows to train AI models, deep learning surrogates that can predict physics at real time. Again, to further facilitate this idea of simulate earlier, broader, more intensely. This is really much everything that I wanted to say about SimScale today, because today is much more about what this enables, the types of engineering work this enables, the exciting engineering work that it enables, and that's really where Joel and Sam are presenters today. So with all of that being said, Joel, I would hand it over to you, and I'm really curious sort of to learn more about the work and what you have to share. And I will. I think now you should be able to present.
Just a quick check on the visual here. All good?
That works.
Okay, fantastic. So thank you for the introduction, David. I'll jump straight in. So really what we're trying to do with SimScale is to understand the challenges around incorporating large air source heat pumps within urban environments. And so apologies for that. So firstly, a little bit of context. This is specifically UK context for everyone to understand. So here in the UK, we have a large decarbonisation drive, and that is spurred on by many things, political as well as financial. And decarbonising heat, which is roughly about a third of the UK's carbon emissions, is a big part of the decarbonisation agenda. So what we're looking at with air source heat networks is a centralised heat production, which allows the industrial scale production of heat, which gives access to things like better refrigerants and more economically sensible resilience approaches. The heat pumps at this scale are highly versatile, so we can do things like split the compressors and the heat exchangers. So the heat exchanger is the unit that takes heat from the air and effectively makes cold air. I like to refer to air source heat pumps as machines that make cold air and heat up water as a byproduct, and really that is what they do. And the compressors really do all of the work. So you get with that splitting, there's an opportunity to optimize the design of the air side equipment so that it meets the needs and matches the circumstance. This is a more cost-effective delivery of heat pumps than the use of the ground or indeed open water. Fans themselves are relatively cheap and inexpensive and light. Ground arrays are expensive and carry risk. And so I think this is one of the reasons that certainly in Denmark, most of the heat network arrays led by heat pumps are almost exclusively air source led, and that is the case in the UK. There are water source networks as well, of course. And the heat network distribution pipe takes heat from these central locations and sort of puts it into a network of pipes at whatever temperature suits the needs to distribute to multiple customers, residential, commercial. And so you're taking all of that challenge of generating heat and putting it in one location to give year-round functionality for resilience, reliability. There's interfaces with cooling, the use of waste heat and diverse heat sources as well. So that's really a rundown. If we look at our projects and our clients, this is specifically for Sam and I in Element Design and JGC, we've been working with heat network providers such as Hemico and Metropolitan and One Energy, Final client, so the University of Cambridge, Goldsmiths University there as well, and the NHS in Scotland on Monklands, and indeed SSE renewables. So what we have projects in front of you that are at different stages of their development. So Chiltern Woods is built, for example, and operational. The hospital is in design and delivery at the moment. The project on the bottom right is particularly sensitive. Anyone with a keen eye for UK listed buildings might be able to find where it is, but it's incorporated into a very challenging landscape. And the Greenwich Peninsula is an iconic gas-led energy centre, which is currently imminently to start being converted to air source heat pumps. And so we have this range, final client, domestic, commercial, anywhere where turning down the rate of burning gas is beneficial. That's our client base. So the crux of the issue with air source heat pumps at this scale is that we can, you can have two of these things. So if you make air source heat pumps bigger, they make less noise, but the air also comes out more slowly, and then the cold air is given less momentum, and dispersion is enhanced. If we have very small fast fans that really eject the air as quickly as they can, and dispersion is improved, we create more noise. So you can imagine in an urban environment, space is at a premium, noise is a challenge, and ultimately of the three, cold air is arguably the most challenging and important from an operational perspective. And so we're trying to round all of these three aspects in a site-specific way. And so what the CFD analysis allows us to do is look at how frequent the risks may arise in a given circumstance, and what those risks might entail in practice, so that value judgments can be made, and indeed spatial configurations altered from first assumptions, which is we typically come in, if I'm going to be candid, people ask us to start modelling the air source heat pump arrays when they already know it doesn't work. So we're not coming in to confirm a really simple configuration or installation. One of the images, I'll just flick back one slide. The image I'll show you on the top there is a 4.6 megawatt array in provincial Denmark. It's been operational for about 7 years, and it is in an industrial estate with no one living near it, on a completely flat plain in western Denmark, which is one of the windiest places consistently windy places on the planet. So it really doesn't have an air dispersion or a noise or a spatial appearance issue. We go to the middle of a city and they're very, very different. So if the cold air doesn't disperse properly or well, the air onto the heat pump will cool down. It stands to reason. In doing so, the heat pump might think might be in an environment that's at +5, but if the air's at -5, the thermodynamics of that compression are much less favourable, and you use more electricity to create the same heat, and there's a real commercial incentive to avoid that. Cold air, if it's made cold enough, can be a real nuisance. I will add the word sometimes on the bullet point there, because actually we are used to, in an external environment, particularly in winter, changing. If you think about stepping around the corner on a windy day and you're suddenly exposed to a wind chill, we're used to big swings in external temperature. However, in the middle of summer, if the air was suddenly 10 degrees colder than ambient and you're wearing shorts and a t-shirt, that's a different situation. Air circulation causing the heat to run out, and if it isn't dispersed at all, the heat pumps will just simply turn off. The air is too cold; they can't take heat from them anymore. The sheltering that we do to screen and visually screen and put noise in can be barriers to dispersion. In fact, they almost inevitably are, and that needs to be iterated. In quite extreme circumstances, we get this a lot in the UK. You get reasonably warm, humid conditions, 10 degrees saturated air. It's possible to super saturate the water. So if you take heat from it, and that is what clouds are, droplets of liquid water suspended in a gas. So it is plausible to make visible plumes if the issues are really badly operated. And then noise. Lastly, here, this is regulated, very tightly regulated in most countries, European certainly. So we can't just always use faster fans to get us out of this challenge, although it is the key issue. So here we have a case study that we're going to focus on, which is in Clapham in South London. So in this instance, there are regulations on the production of carbon emissions and indeed the use of heat networks to mitigate those. And so this is a new build, dense urban environment with limited roofscape, frankly, for air exchange, no ground array, no river. In order to run a commercial, non-fossil fuel-led heat network, this has to be air source heat pumps. 2,500 homes in central London. This is a valuable piece of real estate, but the UK is subsidising these installations. So it's subsidised to the tune of £3.7 million. That does not pay for the heat network, but it certainly erodes the extra over cost of the capital of the plant, which is about 3 megawatts spread over 16 coolers on the 6 rooftops. Key challenge here really is that we are in a residential urban environment. If you look at the render, you can see these kind of wells that really want to attract cold air. For those, I'm guessing most people on the call know, as you cool air down, it gets more dense, less buoyant, and wants to find places to sink into. And an issue as well, of course, under certain wind conditions, we can see that contamination of rejected air. Cold air, one way to think of it, is a pollutant. I mean, if you could see it, like you do a gas boiler plume on a cold day, you would see it being the discharge of one array potentially sucked into the other and having a magnifying effect in a certain wind direction. And the last point on there, on the visual, the roof terraces. So the penthouses of these developments are often among the highest value, and we're putting the source of cold air effectively directly above them, and we did need to manage where and if cold air was manifesting itself and staying in the vicinity of these roof terraces, because they could imagine them being quite inhospitable if this is not managed well and correctly. So without further ado, I will ask Dave to pass over to Sam, I would leave it on here and then pass over to Sam.
Thank you, Joel. I'd like to talk about sort of the nuts and bolts when it comes to the geometric modelling and also the CFD simulations, the challenges that we face, how we go through sort of validating and substantiating our work, and how we go about doing that. So a bit of a whistle-stop tour. So what we're ultimately trying to do is simulate a certainty of outcomes. There's expectations that we have, both in the way in which we expect the heat exchangers to run in isolation, but also in context of the projects that we're running within the built environment. We tend to repeat a process which I wrote down the other day, and it was quite surprising how often this happens. Is essentially first and foremost we need to simplify the models. If those of you aren't familiar with BIM models and the complexity of those, they often are a much higher level of detail that's required for something like a CFD study, and they also can contain thousands, hundreds of thousands, or even tens of thousands of individual components, which just aren't necessary when it comes to the simplification that we require. Then we go through this process of running and failing. We fail a lot when we come to do simulations, because our expectations are often, they succumb to issues and mitigations that we just can't quite get around. Funny enough, every project that we've done so far, we've never passed the first simulation study successfully. We've gone on to do iterations of the geometry and changes to get to the goal that we want to achieve. So we go through this fail cycle, find a lot of dead ends to find the end that works, and we go through the iteration process. So the iteration process, as Joel has already sort of touched on, might be the creation of physical barriers. It might be the increase of the inlet into an array that we've modelled. So we go through these geometric changes, and then ultimately we're working towards success at this point. We're starting to see positive changes towards the model and the simulation stability, and we're starting to win the project over. So I'm going to, if David, you could flitch the presentation over to me now. I'm going to go into a few programs and just explain in a bit more detail.
Did that work?
you.
I think now you should be able to present.
Yeah.
There we go. Yes, we can see the
Okay.
CAD model.
Great, thank you very much. So first and foremost, we're looking at simplifying geometry. So as you can see here, this is representative of the Clapham project that Joel was referring to. What we've got is a very low level of detail of the surrounding built environment. And then we've got a more high level of detail of the building in question, which is what we can see here. Now you can see we've got parapets, we've got terraces, we've got all the ins and outs and the wells of this building. Now that's critical for us because it's where the detail lies, and the devil's in the detail for us when it comes to the simulations. The scale in which we actually model. So this is a selection of buildings, actually, not obviously all the buildings, because there's a lot more buildings in the built environment around here. But what we don't model is everything. So we're not interested in trees because of the sort of transparency when it comes to the air and their complication when it comes to the CFD. We don't have roads. We don't have every single building. We're interested in buildings that might be sheltering the heat exchangers, which is what we have here. We use SolidWorks for the geometric modeling for two reasons. One, because we're good at it, but also secondly, because there's actually an API plugin for SimScale and SolidWorks, which means that when I create my geometry in SimScale, I can, with a click of a few buttons, push it to the online SimScale platform. So that's really helpful when it comes to iterations that we're making. So our domain itself is actually quite large. So in fact, this one's smaller than usual. This is 750 meters by 750 by 150 meters. We've done domains, fluid domains here that have gone up to 2 kilometers. And it all depends on how much of the built environment we feel like is sensible to model that might be making impact or not on the simulation itself. So going over to SimScale, I just want to flick through a few examples that we've got here. This is the model inside SimScale. What I really love about SimScale when it comes to the meshing is the fact that the meshing is adaptive. So we can see this high density mesh in areas that we are particularly interested in. Now that's automatic because we've got high levels of detail in those locations anyway. So SimScale is automatically doing us a great favor here in having higher mesh densities in those locations. And then as the further you move away from the more complex geometry, it automatically is reducing the level of detail of that meshing, which is super helpful. One thing which we do need to achieve as well when it comes to simplification is heat exchangers. So this is a representative of a heat exchanger. Now, what you would normally expect to see here, let me just collapse this because it looks a bit strange exploded. What you'd normally expect to see here is a load of circular fans, and many of them. There might be 12 fans in this one array here. So we do a few things. We simplify the geometry and merge the areas of the fans. We also merge the enclosures, and we reduce the complexity of the geometry, but also reduce the complexity of the simulation. When it comes to setting up a simulation, what we are applying to these volumes is momentum sources and heat sources. And the less of those we have, the better. It reduces on the complexity of the computational processing power of the simulation. It means we get to either fail or succeed quicker, and it's a really great saving. I've seen a few variations of this type of simplification done on other projects by other companies. What we do different here is that we've got these strips of represented volumes. It's really important that we maintain the same surface area of the fans throughout the simulation. So what do we do first? Well, what's kind of linked to what Joel was referring to this sort of open field in Denmark, where they've got the best case scenario of where you might want to put a heat pump. What we do first and foremost is we test the expectations of the specified heat pump or heat exchanger. And we do that by creating this open field test, which is what this is. It is a single heat exchanger in a field, relatively small domain. And what we do is we run a very simple test on it. I won't go into every piece of detail here, but one of the things that we see here as a positive outcome is that we're seeing good air dispersion as the fans are jetting the colder air upwards. We're seeing that get carried away with the ambient air and also mixing. So that means we've probably most likely mitigated the risk of recirculation and contamination of the cold air back into the intake. So we do this, we do it for our own sanity to make sure that we're expecting the correct sort of outcomes when we start to put this into the built environment. But also importantly, we're comparing the outcomes of this with the data sheets that we get from the suppliers and the manufacturers of the heat exchangers. So is what they're saying what we are seeing in our simulations? And not to say someone's incorrect, but we need to make sure that those two pieces of information are paired together before we move on to the next stages. One of those next stages is to complete the field test again, but do it in a much a scaled up manner. So what we've got here is we've got heat exchangers in a large bank, and this is more representative of what we might be seeing at an energy center. And interestingly, what we see here is something that we don't want to happen, is that we're seeing contamination of the cold air recirculating back into the heat exchanger. And this effect is something that is a phenomenon we see regularly for large-scale heat pumps, exchange arrays such as this, where there's a very large area effect that's occurring. We've got large bulk volumes of air, we've got large bulk volumes of cold dense air, which is recirculating. So this is a part of the iteration process as well. We're piecing the puzzle piece together here and understanding what might be occurring when we come to do the full simulation itself. So just moving on, what we do a lot, as I mentioned, is fail, and this is a great example of something failing in the Clapham model. We are seeing here a large portion of cold air dumping off the side of the building. It's not only dumping off the side of the building to the pedestrian level, which is going to be an issue for pedestrian cold comfort. It's also going to be an issue for the people that have bought penthouses either side here, where their rather expensive terraces are receiving some rather cold air, which would be quite constant. So this is something which we see a lot of. We're also experiencing, it's not shown in this model, but as Joel was mentioning, some phenomenon, particularly in this model, where we were seeing a large dump of cold air falling into this well. Now, as you can imagine, there's no wind blowing over the top of that well, encouraging the mixing of that air. So our goal there is to try and mitigate that risk entirely at an early stage, so we completely avoided it. So this is a great example of something failing. Now moving on to something that's a bit more successful, an example here of a study, and essentially the exact same geometry, no particular iterative change in the geometry here. But what we can see is, and it starts to experience, is the more suitable and correct and desirable dispersion of the air into the atmosphere, which is what we want to see. So that's a real quick whistle stop of SolidWorks to SimScale and the kind of things that we're looking for. David, if you could flick back to Joel, but I'm going to keep talking for a moment, if that's possible, and we can reshare the presentation. Or if you can move on to the next slide, Joel. So what does success look like? So there's a few things Joel has already touched on at the moment. These are the sort of things that we want to pick up on when we're completing our simulations. So first and foremost, the first thing is the rejected air is mixing well into the ambient environment. We want to see these plumes rising vertically. Occasionally we're jetting downwards with the fans. However, more often than not, we're jetting up into the atmosphere. So mixing, despite jetting up or jetting down, is what we're looking for. When it comes to noise, if we're overworking the fans and the pressure differential is outside of the operating specified differential from the fan supplier, we might find that we're starting to encourage far more noise than is acceptable. So what we're looking at is these suitable pressure differentials above the top of the heat exchanger and below in the intake as well. Next slide, please, Joel. There's a few indications when it comes to recirculation that we're doing the right thing. One of them is that we can notice that the average inlet temperature on the underside of the heat exchangers is as close as possible to the ambient temperature. Now, if we see that the average has dropped substantially, it's a very it's very likely that we're seeing some recirculation. That view there is directly underneath the heat exchanger, clipped on all sides. So all we're seeing there is the average inlet temperature of the model. And that's one of the first things that fundamentally I go to see that we're on the right track. And there's a great example there of something we don't want to occur, which is this pedestrian level rejected air, which is approximately colder than, on something like 3 degrees colder than ambient. That's when you start to feel the difference between the ambient air and the colder air. And you can see from the sprawl of that, it does spread significantly across into the environment. That's a couple of 100 meters. It obviously drops in temperature closer to the heat exchangers and warms up, and it starts to mix with the ambient air. But again, it's a non-desirable. Moving on to the next one, please. And then finally, again, you know, something where we're noticing a large plume, sorry, not large plume, a large volume of air which is lower than 7 degrees below ambient is of course a risk of physical plumes, which is what Joel has touched on when it comes to the formation of essentially clouds, or, you know, we'll probably call that fog at low level, but yeah, it's a complete undesirable. And then what we need to do is we need to make sure that all of those above are replicated for all wind conditions and speeds. So we'll go through and we'll complete a set of studies then for 4 wind directions and also 3 or 4 different variations of wind speeds. One difficult issue to overcome is when we have a no wind situation, which can happen in the UK. It's one of the situations which we can't always solve that problem, particularly in the built environment. We often find that the no wind conditions are one of the few that we can't always overcome. However, we have also done so in the past. So move on to the next slide, please. So this is a great example of something which was probably the worst place to put a heat exchanger. And we're really up for the challenge of resolving that. This is a civic building, a council building in Hillingdon, which is Uxbridge, far west London, near Heathrow. This is it was a decarbonisation of all the civic and council buildings in that area by the local council, funded by the government decarbonisation scheme. And they had identified various locations to put some heat pumps. There were some obvious ones, like the roof, great, perfect place to put a heat pump in this particular instance. And then some not so desirable locations, such as in this service area behind the back of the civic centre. So that was a really tricky situation where we're running studies, and, you know, the issue here is that essentially it's not below ground, but it's surrounded all the way around, and it's creating this sort of well environment. Now, we were witnessing a few things. The obvious one is that the air was going up and then it was coming down, and it was sitting in that well, and we were really encouraging a huge amount of recirculation. So there is always a solution, and in this particular solution, it was to start to encourage the mixing of the air at a high level, at a high elevation, in a point in which the wind was having an effect on the rejected air. So what we did was we simulated the idea of adding these snorkels to the heat exchangers. So what you can see in the sort of clay rendered image there is these snorkels that are on top of the heat exchangers, and it solved the problem. So we're really proud of that of that solution. I think from one of the hardest ones we've done, actually, probably one of the smallest, but also one of the hardest ones that we did. And it's great to see that project is now underway. There's some examples there, some photos there of the installation of the heat exchangers. These ones that they're lifting here are going up to the roof. But as soon as they cleared this area, we can already see the services and infrastructure going in for the service yard heat exchangers. So a really interesting problem with a very interesting solution.
I'll just pick up on this just to mention that that's the air dispersion, which of course is one of 3 of the core challenges. So here, of course, spatially, you can see how tight that is, and the closer we put these units to each other and the larger they are, this is driven by the capacity requirements of what is a very, very sizable building. This building is also listed, which means it has sort of heritage protections, and that was a particular challenge. And I don't think the snorkels look quite as stark as they do in that image, but they perform another really important function. So as we turn up the velocity of the fans, which really we had to do in this circumstance, the noise goes up, the aerodynamic noise of course goes up. So these and what's not seen in white to the bottom left of the clay render there is a residential block. So they're existing flats, people live there, and there are regulations rightly around industrial and commercial noise adjacent to residential units. So they are effectively continuous and open noise attenuators. So the snorkels lift the point of mixing as well as attenuating the noise, enabling us to run the air faster. All of that iterated through many sort of options and real project context considerations such as that. So we're not only ever dealing with the air, it's one of those three core issues. And I think it's safe to say we enjoy this. We think this is a really important aspect of the energy transition. I certainly do, and I think most European nations and a lot of nations around the world are on this, somewhere on this journey. We haven't found a silver bullet, is I guess my point. You know, it's been a site-specific location in each and every environment, and if there were one, that would be great. But we'll report back maybe in a few years. So I'm just moving on. So we have this link to data centers really, and I think an image in the top right there, which is a research park, and this is a feasibility study that we did where the heat from a data center is put into a network of pipes to be upgraded and used for the research park. That isn't always sensible or possible for either legal, technical, or financial reasons. And so most data centers, sorry, I should have mentioned, the building in the bottom left there is a 2 megawatt data center, turning out 2 megawatts of heat continually. But actually, in most instances, the heat generated by data centers is a pollutant, and all of the issues that we've just described transfer almost entirely, with the exception of the comfort, I would say. But you know, warm air can be a pollutant that can interfere with other people's heat rejection in data centers, and the computation is not decreasing; it's increasing. I mean, the use of AI increases computational load. We rely on computational load every time we run a SimScale model, for example, and that's what we do. We turn electrons into heat somewhere so that we can evaluate this. And I think that this approach and that consideration is as important really for data centers, with the key difference that when you warm air up, it does want to go up. It gets more buoyant, not less buoyant. So actually, I think the solutions might be more available and might be less challenging to find in truth. Of course, CFD analyses are used to look at air dispersion around racks and within data centers. This isn't something that we've done as a business, but actually in this context, it's probably as important a consideration to their operation. So the key points of this really is that network scale SSE pumps are a very important part of the energy transition. I think they're going to increase in their prevalence and their deployment, particularly in dense urban environments. They produce large volumes of cold air, typically about 30 cubic meters a second for every 300 kilowatts. So sort of 100 cubic meters a second for every megawatt, and that can be very challenging to deal with. CFD is probably the best tool that I think we have to balance those contradictory measures between noise and size and air dispersion. I can't think of any other way to do this. We have to have a project where we've done physical testing. That's expensive, it's time consuming, and obviously computation is the tool there. And I put there's always an answer, and then I had to quickly caveat that. You know, the Hillingdon scheme and another similar to it, you look at it and think, this brief isn't achievable. You know, we will try our best and we have a very open mind. And actually, when the recirculation cells break and a solution presents itself and the acoustics work and the capacity works, it's very rewarding. And so far, at least, we've managed to find an answer, and to see these projects being built out is fantastic. So I think that largely wraps us up. If we have a project that we can help with and take this learning and this experience, then please do get in contact.
Awesome. Joel, Sam, really, thank you so much for sharing. If you don't mind, just like to cap off with 2 to 3 questions. Joel, what I found fascinating what you said earlier, because for context, SimScale and the SimScale engineering community operates globally, and we work with many different sort of AC and civil engineering firms all over the globe. And you said something interesting there. You said earlier that the projects you've shown, there were some decarb sort of funding schemes, so they were funded, and so there was a incentivized development for that. But are the developers of those projects, are they sort of aware of the of the engineering needed to make a heat pump, an air source heat pump network really work? Because you said something earlier along the lines of you typically come in when something doesn't work. So what's your sense of the awareness around that particular piece of technology in development projects? Are people aware that this is something you should engineer before, or is it really something where you typically come in for troubleshooting?
I think we're not coming in for troubleshooting when something's being built. We're coming, so obviously you have stages of design from feasibility, concept, detailed and technical. And somewhere along that line, people manage risk registers in a real project, and the risks can be anything from financial to governance to the whole basket. And I think more people are sitting in those discussions earlier, asking about cold air. And typically this will be born out of experience. I don't know of a scheme, but we had feedback from one of the larger European manufacturers that there was an installation, they did proclaim not their own, and I'm not name dropping anyone, where it failed because of air recirculation problems. And you can imagine, looking at the scale of these things, they're not cheap. The solutions in practice on the ground are probably not available as retrofits, and there are major issues that will result from that. So I think Sam and I have been doing this for over 5 years. In the UK, the net zero commitment for 2050 was declared in 2019. Regulation took a little bit of time to catch up. It now has caught up. The funding schemes that support the developments meeting this are picking up, and the number of inquiries and questions and suggestions are also increasing, but the experience isn't there. So I think what we're getting is early stage concept designs from architects and engineering teams that perhaps haven't thought about these issues from the start. And this is quite extreme in some instances. I had a much smaller project inquiry come to us. It had planning, it had listed building consent, and the air source heat pump was literally in a completely enclosed box with a roof. So people, that is an indication of the level of misunderstanding of what these pieces of equipment do. If they don't move air, they don't work. So I think experience is increasing, and this is not just the UK, of course. This is across the board. But there are, just to reiterate to everyone, there are many megawatts, tens of megawatts, hundreds of megawatts of working grid scale air source heat pumps around Europe. And most of them look like the one in Denmark. Incorporating them into the urban environment, where the land value is typically higher and the risks are therefore higher, is what this assessment is about.
Fascinating. And then one double click, Joel. I liked when you talked about mitigating risk. I mean, it's the perfect example of engineering work is always about trade-off, right? Like typically, it's sort of you talked about the different risks you are mitigating, and you talked about noise, you talked about the visible plumes, you talked about cold air, like pedestrian comfort, I suppose, and then last but not least, energy efficiency, that you actually get the energy efficiency out of the system that it was designed to. Any particular order of those, or also because you have much more experience with those installations than possibly other folks on the call. Any particular order, like a thing you look first, and if we, I don't know, get a bunch of pedestrians cold, that's not so critical, or how do you think about like the order of those risks?
I think that's a great question, and the answer is it depends. It depends who you are within a project, of course, right? I mean, what I would say about CFD modeling, like any modeling tool, is it is imperfect, right? Any model every model is wrong. It's a question of how much by, and maybe with you, David, and SimScale, it's not what you want to hear, but that we inherently know that. And so we're advising and informing in a quantified way decisions, real practical decisions. And the modeling that we've got has an element of a conservative approach, and because we have to err on that side. And then we descriptively try to rationalize and explore the practical issues that may result from those conservative results. So I think, look, we get projects where some people, particularly the funding situation is really important, and therefore the efficiency, the COP, because it is marginal. You know, a 0.1 difference in a COP can be the difference between the project making financial sense or not. These things, again, people take a risk-based approach financially, so that can be make or break for a project. If you're the neighbour, and we have had this on a project through the planning process where a neighbour flagged the potential risk of coal pollution to them, and that became a planning issue. So at that point, that was about pedestrian comfort, became almost a bit of a make or break. And then reputationally, I think the production of visible plumes for some clients is, it's not plausible. You know, if you have gas plumes coming from and they're cold, I mean, it's quite strange. I see a lot of energy centres around with plenty of visible plumes coming out the top from gas combustion. So I don't quite agree with that one myself, but at low level maybe. So I think if I was to put them in hierarchy, then actually interestingly efficiency because money makes the world go round, right? And that efficiency equals electricity equals cash.
And there's occasions when some of the risks that we're talking about might be secondary or tertiary effects of one that might be primary. So you might have, if you don't get recirculation, are you going to end up with pedestrian cold discomfort because you're not creating a plume that's then sinking down to pedestrian level? So, you know, a lot of them are interlinked with each other.
Yeah, I mean, my like a 10-second addition round is like working with so many architectural firms. I think our sense is also that there's more and more consideration of that, right? And more sort of awareness of that it's not, you know, that there's that these things matter more and more, and that the drive for net zero buildings sort of, I think, pushes some of that simulation work, some of those considerations earlier and earlier. But really where my question came from is the fact that we see it in different locations and different regions at different levels of, I guess, awareness and consideration. So fascinating to hear. We've still a few minutes left, and there's more questions from the audience, and I have one more. But just looking at the audience, there's one question around mitigating the issues we've heard, the risks with heat pumps. Any thoughts on, is it feasible to use thermal batteries to heat water and circulate around? So have you ever, experienced that or using that as a strategy?
Yeah. Okay. So actually, the example, the short answer is yes. I mean, like most things that you can technically conceive, they're possible. Are they sensible? When I say sensible, I mean economically viable and spatially and all that kind of stuff. That is our fire alarm, and it shouldn't be going off right now. That's a banding sign fire alarm. Oh, it has stopped. It has stopped. That was thankfully for that. Okay. So coming back, the example I showed in Denmark had all manner of different heat sources. One of which was an 11,000 volt electric boiler, which is a heat battery, with a big thermal storage in water in that instance. And so that's there to take up the excess electrical energy made by Danish wind farms. So the economics are all dictated by the electricity pricing, which is dictated by the electricity sources, if we're talking about using electricity. With heat pumps, they will always use less electricity for the same outcome. They don't take electricity and turn it to heat. They use electricity to take heat from somewhere useless and make it useful. They pump heat. That clues in the name. So I think yes, you can use more electricity for the same outcome, and that intermittency that thermal storage in particular assists with is an interesting factor. And I think we are seeing that in most energy centres. The energy centres that I showed earlier in the scheme will also have big electric boilers to take out, say, negatively priced electricity or ultra low priced electricity. But the heat pumps are going to reduce demand considerably for the remainder of the time when electricity has more of a higher cost.
Fascinating. Yeah. One to two more questions. And Joel, by the way, your security is of high concern to all of us. So if there's somewhere a fire, Joel, please, take care of yourself. So just want to put this out there. I don't want to hear, as much as I appreciate the commitment to this presentation, it shouldn't go so far to, endure a fire.
I think it was a false alarm, and I apologize.
I think you should finish the webinar.
Sam said that. I didn't say that. Maybe more on the CFD side, where I also have one more question. One question from the audience is, any experience with sort of actual measurements then on the installations that you've done, as in that, I don't know, a developer that commissioned those studies wanted to have on-site measurements, something that you can talk about, like measurements versus CFD. Any insights?
Yeah, so we have a scheme here in central Cambridge. I'm based in Cambridge in the UK, and it's a smaller scheme. It's a 300 kilowatt scheme, but the heat pumps are not quite as poorly positioned as in Hillingdon, and it's my project, so I'm responsible for it. And the risk was known right from the outset, and so in that instance, the modelling gave a good indication that we were in a strong place. But we built a one-to-one factory mock-up in the factory prior to delivery to site of the temporary heat pump, the exact dry air cooler configuration, and actually it resulted in I'd pushed on the back of the modelling for a physical separator that was horizontal. The architects had some pushback. We tested it on the factory acceptance test, and I got my shelf back following the factory acceptance test with temperature measurements and with smoke testing at the same time. The installation is now installed. It was commissioned last week. It's great commissioning things just before Christmas. But I think so far on this level, I think coming back to the conservative modelling, I think with the modelling that we're doing, if it works well in the model, it's likely to work well in practice. And we tend not to make recommendations that aren't working well in the model. So if things are working well, the need to return and look back at temperature modelling for our sake as consultants is lower. Clearly, all built installations are measuring their temperatures of their inlets and their discharges. And if there were a problem, I'm pretty certain we would get a phone call. And it mightn't be pleasant, so that's where I'm pitching that one. No news is good news, David.
That type of bad news tends to travel fast. Being in the simulation business, I know that as well. Nice. Yeah. And then just the last question, Sam. The simulation workflow you've shown. We all understand there's several simulation engineers in the audience, but we all understand there's some initial setup time, as in you get a BIM model that might or might not be well prepared for the types of simulations you intend to run. Once the setup is there, you've shown it, and then I assume there's some, you do studies on positioning or fan speeds and whatnot. Could you talk about how long does it take you to sort of like for one iteration to go from one, you tested something, you don't like how it looks like, on the same wind direction, the same conditions. How long does it take you to do one iteration?
So it depends on the project, but realistically, I can get an iteration done within an hour. I can get an iteration running, and then within a couple of hours, I've either got a fail or a success, and moving from there. There's a few projects we've worked on in the past where the iterations have been landscape, and that was quite a tricky process because the failures weren't coming from the expectations of what should be happening with the air, but actually with the stability of the geometric modelling and then the meshing. So that was quite a challenge that we had to consistently iterate, that landscape. So that was taking days. But typically speaking, within an hour, I can get an answer.
And then to cap it off with the last question, the types of CFD results you've shown us, are those then some that you actually review also with the client, with the developer looking at it? Is it something you actively discuss, or is it more like you're doing your internal studies and then you come up with a design recommendation?
Yeah, so we will produce a final report, and in that final report we will share in the appendix all the results that we've got, ending a few because there is a lot of them. So we'll end up giving people velocities and temperatures and average temperatures. There's some that just aren't pertinent, and we just won't necessarily have to share it. On occasions where we're seeing a phenomenon that we don't expect to see anywhere else, we might start to share some details and results that are very specific to what's happening. But typically speaking, it's the same set of results that we're creating every time, and just sort of repeating that.
What I'd add to that is transparency is key. You know, we're being asked to model this because there's a concern or an innovative proposal, and those innovations, no innovation is without risk, or it's not innovation almost by definition. And so when we're given a chance, which is most projects, people are concerned about this issue, transparency is there. You know, we're very transparent about the conservative elements of the approach. For example, the wind is modeled as a static condition. That isn't how it works in practice. Wind is erratic and chaotic. It changes direction and it changes speed. That actually assists dispersion, but we can't resolve the model without having a static condition. So we're very, very clear about this, and we share the outcomes. And I think what we add is that bit of commentary and the assistance with the interpretation of the models overlaying onto a practical consideration.
As the old saying goes, all models are wrong, but some are useful. Yes. Yeah. Joel, Sam, again, thank you so much. I know, again, Joel, you said it earlier, commissioning in the last days before the holiday season. So we really appreciate it. In the name of the audience, in the name of the SimScale community, thank you so much for making the time, sharing some of that work. This will be available as a recording soon for rewatching for the audience. And so, Joel, Sam, thank you so much for the time. And to the audience, thanks for joining us, and hope to see you soon in one of the next webinars.
Thank you very much.
Great. Thank you, David.